All right. Who knows if it's actually on? Let's see. It's saying live 11 seconds. So we're good on this wonderful middle of the week live broadcast. Welcome to the stream. We're going to get a little bit of music going early because you're watching this from the US and you're watching it from work. I'm sorry, but yeah. Hopefully, we'll be able to get through some of this stuff and I don't know, ease your pain on this uh, Wednesday before the holiday. If you're not in the US and you're watching this, I don't know, it's probably like 7, 8 o'clock, maybe in the middle of the night, which I ask, like, well, I don't know, it might be pretty good. It might put you to sleep. Maybe you have sleeping problems and you need just a, like, low, mildly entertaining thing to just kind of like ramble on so you can drift off into sleep. Just know that if you fall asleep while watching this, you will be um, dreaming about Siemens PLCs, and only weirdos like me do that, I guess. So, uh, but welcome to the stream. Looks like we're going. Uh, Honestly, this is one of those things that I wanted to get a stream this week, but I was going to be traveling for most of the rest of the week, and so wanted to get something up just so that we could get some content out there for the rest of this week. So when you get back again, uh, you get back into the week next week, you have something to kind of work on, and hopefully you will be able to use some of the content on this to be able to help you out. So if you haven't looked at the title, and I want to make sure that audio or the music isn't too loud, but if you haven't looked at the title, uh, this is a stream that is kind of just about really about a couple of topics that have been brought up in comments on previous videos. And one of them is a better explanation of what an in-out parameter is. For a couple of times we have uh, talked about function blocks and the interface into them, and one of the things that comes up because it's not really used commonly is the in-out parameter. So I want to talk about that. I want to talk. I would like to try and talk about using PLCSIM, but I realized I didn't have it actually installed, because if you do a downloadable install, it doesn't come default on the disk. So you actually have to install um, totally separate ISO in order to get the PLC sim installed. And I didn't realize that I didn't have that installed. And so I literally finished up that install like, I don't know, like 5 minutes ago. So who knows if it's actually going to work. Um, but if we can get that working, we'll do that. But the second thing, or I guess the third, the primary thing that we'll be talking about the most will be a drives topic that has come up a couple of times amongst not just the kind of streams and talking about the comment sections on some of the videos, but also in a lot of the classes that I have given in real life through the years. There's been a topic of how to make two drives load share, and we're going to take that and turn it up even more, um, and actually do 4 drives. And so um, I had the privilege of, when I came out of college back too long ago, to work at a very large coal mine in Alabama. And if you didn't know that there was coal mining in Alabama, well, you're pretty much everyone but like 10 people. So, but yes, my first out of college job was as an electrical engineer at a coal mine, and there were in in this mine there were belts that were up to a mile and a half long, um, and all the way down to a few thousand feet or so. And when I say belts, I mean conveyor belts that are 60 inches wide, that are carrying tons and tons of coal, just constantly, continuously. And they used a technology to where they had 4 drives that were set up, and then they would load share they would have two driven rolls, and then they would lace in between the rolls, and would be able to do the kind of load sharing between 4 drives on 2 axes, or two not axes, axles, two rolls. So a drive on each, and we're going to talk about that, and that's one of those topics that is can be taken to a lot of different places, and so I wanted to go through that, and so stick around as we kind of get through all sorts of stuff on that. Um, but so without further ado, I want to start out with kind of an easier topic, talking about in-outs. I'm gonna go over here to a screen over here, and we're gonna talk about the in-out parameters. And honestly, the best way to do this is show you how I have a block that uses the technology. And if you come on stream, like I see a couple of viewers coming through, be sure to like the stream just to get more people out there. Hopefully no one's having to actually really work too hard on this Wednesday, but be sure to drop a comment if you come in and say hey. But we're gonna go through, and I'm gonna show you an example of how I have used an in-out parameter. So this is a project that I'm actually still working on, and so it's kind of in its probably about 50% state right now. I've tested the communications, I've tested the basic functionality of some of the stuff in here, but in essence, it has 5 remote stations that are communicating, and there's a pump out there. There is a remote pump out in the field, and these are going to be cascaded together, so multi-stage pumping application over the course of probably about 5 or 6 miles. So a pretty cool project, but the reason I bring this one up is because I have a block in it that I have made that resides on all of the individual remote stations, called multi-stage pump. And it is a multi-instance function block that, as you can see here, because of this top little bar here, it is attached to the project library. And I'll pull this up over in the side here. And so you can see I've got a couple of different things that I'm trying to do the right way and set up these reusable blocks. And so I've written this one multi-instance function block that I'm going to put on all of these pumps. And the intent of it was to provide just everything you need to bring in for these kind of remote pump systems. And let's take a look at the interface, because that's where it kind of gets cool. So you have your standard inputs, outputs, static that's being used inside of the data, your temp, and then constants. So by the way, I don't know if anybody else uses like a no op or an always on bit in any of their code, but you can always put a constant of always on as true, or always off or no op as false. Put a constant into your function block, and then you can use that in your code, and you have the ability to, no matter if you're troubleshooting something and you're wanting to like no op something out, include that in your function block. So constants, I don't think I've ever talked about constants in any of the function block videos, but because I feel like they're pretty basic or kind of self-explanatory, but they don't change. And so you cannot change a constant. You cannot write to it. You cannot, I mean, I guess you can read it, but they are defined, and that's it. They are always in. But so if you want something else like a constant 100%, or one of the ways that I've used a constant in another block is I have machine states. And so in a state machine, you have a variable that tells you what state you are in. And sometimes you want those states to be like not just a number, you want them to make sense. And so what you can do is up in your constant for that function block, you can go through and define all of those states, like running, startup, overcurrent, undercurrent, whatever. You can define those states as a name and then their constant values, say like 50, 51, 52, 53, 30, 31, 32. And then when you use those values in your code, all you're having to do is type in, hey, if I am in a comparator, if my state is in overload, then you can do that. So yeah, so that's what a constant is, and that's completely random. But what we really wanted to talk about was this in out, and I had described it before as kind of in the kind of object oriented realm of everything. I'm gonna get this off. Like, I'm ADD and I can see myself like over here on this side, like messing with me. So in the like object oriented world, or C++, C sharp, like those type of worlds, you have like you can pass a value by reference, and or you can pass a value, pass by value, pass by reference, which in that programming world, if you pass it by reference, it doesn't actually create any, it doesn't use up any temporary memory on your processor. If you pass it by value, then it will do a context in the context switch between the two programs. So your global or your global scope into your program scope, it will actually create a copy of whatever that value is, shift into your other function, and then use that, and then it's gone. It has to be used inside of that function. Basically anything outside of the global scope, or anything in the global scope, doesn't receive that unless you pass it back in a return value or do something intentional. Well, in out is the same thing as passing it by reference. And so passing it by reference in a programming term would be, you're really technically just giving the function a pointer to the value, or pointer to the location that you're trying to use. So whatever it is that you're passing in, if you're passing in another object, for example, and this is way outside, I'm kind of, I guess, speaking to people that have experiences outside of PLCs. And so if you kind of don't know what I'm talking about, don't worry about it, because like as you kind of move through PLCs and you start to grow, you will kind of grow into these concepts of oh, if I'm using a function block, if you ever go over into object-oriented programming, like in like a .NET programming or anything like that, you'll have something to fall back on. So all that to say, an in-out makes it to where inside your function block, it has access to the data. It can do whatever it wants to, and without passing through either a output or static, that it will actually change the values in the actual global block. And there's some distinct advantages to being able to do this sort of stuff. And the biggest advantage is that, for example, I'm going to show you this. In an instance where I have this set up to where the communication block that this is using is essentially going, I'll show it to you. There's this block called remote updates, and I've shown this in another video, but of course, there's going to be something that's not quite right. But this goes through and just sits and uses puts and gets commands to update data blocks in each of the PLCs. So it will put the master data into the remote PLC, and so it's going to put this data block here into the remote PLC, and then it is going to get the local data. So everything that's being populated by my block, it's going to get that data and pull it back and give it access to the master system. Because in a multi-stage pump system, you're going to need to be able to balance out loads, and sometimes you'll have some pumps that, depending on the pressures and everything, might not be doing their fair share of everything, and so you have to have a master control to be able to stamp down pressure, or like balance out pressure across the whole pipe, especially on this pipe, which is miles long. So the reason we use in-outs is because I want this sort of setup to be exactly the same on every remote block. So every remote block has a DB, in this case DB4. Don't make me a liar. So I guess this is the master data stuff. Yeah, so it's DB5. So it doesn't quite work out like I had intended it to, but the point is that there is a block there that that we're going to bring in, and let me show on if I actually called this so I can show you how this is. Yeah, I have. So this is actually on this remote station, remote 2, that has this block. And so this is the instance call of that block. And what I'm doing is I'm supplying it some of the local data. So like the actual push buttons. So that's why you see you have an input, you have this output. And I'll talk about that in a second, because that will have to do with some of the other stuff that we're doing. But you have inputs and outputs, and then all you have are these data blocks. And these data blocks are the same thing that is getting updated by this other system. So it's in this global scope so that it has access to the other system really easily. And the reason I have to use an in-out instead of just pointing that to the instance data block of this is because if I were to change that, every instance data block, or I could never make it to where this data block was actually the same on every unit. It would inherently, from the master's perspective, it would inherently be looking at different data. So I would not be able to just straight reuse this function block that I made. And it's kind of a little bit of what's it called? I guess nitpicky sort of difference, but it very much makes a difference in memory consumption as well. Because when you bring in this data in as like an input, first of all, you can't change an input. Second of all, it's making essentially a copy inside. It's using working memory up. Whereas if you have this other data block that's already called, it's not going to be using up memory again. It's just pointing to that other location, like we talked about in object-oriented location. So I'll show you how I use it inside of this in-out. So you notice I have a PLC data type that is custom PLC data type. This is the actual structure of that data block. So if I were to go to this, if I were to actually go to this local pump data status, so what we're using here is station data dot remote station local data, and I'll show you what it means. So I have this data type here. So I have this data block, station data, and it is pointing to this place. So station data should always be DB1, and then it's always going to be pointing to this first thing. And I realize over here on my other thing, I realized why those data blocks were not the same like it was supposed to be. So if we look at remote station 2 transfer, which is this, this is a put. We're putting into remote station 2 data, which is this DB4. We're putting that into the pointer DB10, and we go down through here, DB10. I had those mixed up a second ago in my brain. This is the master's local data block that it's kind of giving its data that it can use, because you don't want to be like pulling this, so there has to be some sort of like temporary data. So this is the remote pointer. So the way these puts and gets is you say a get is going to point to remote data, and you're going to get the data and you're going to get it into the local data block, and that's what's here. So get the data from address 1 and put it into the read data block. So that's what get does. Put, just the opposite. It's going to put the local data block into the address. So it's putting it into the pointer. And if you notice, if you go down through here, all of these pointers are the same. And that is because I'm using that the INOUT, and I've defined this station data. I've defined this station data block, and inside of it, I have a data type that is my custom PLC data type: pump remote master data, pump remote local data. And so in every one, DB1 is this data. And I realized that might not actually be working, because but so every one of these is pointing to the same data block. And get back. Always organize your programs, because this program is a little bit complicated, because it has 6 PLCs and 6 drives, and they're all on one network, but they're all not communicating. It's been an interesting concept, or interesting time of me kind of like fully wrapping my head around the best way to do all of this stuff. But anyway, so our multi-stage pump, all it does is it's bringing in from, as an in-out, this station data type. So we bring this in, and now we have access to all of this data inside our data block, and we can do whatever we want to do with it. And the subtle difference between static and in-out variables is that in-out variables, you can freely parameterize what goes into that input. It's an input. A regular input, though, you cannot write to it. Meaning, if I take this flow raw input I'm gonna edit this. Well, I guess I can't because I've got it up in a different place. Um, the if I were to try to write to this flow raw input, it wouldn't compile because flow raw input is an input into this data block. It would throw an error and say, hey, you can't do that. If I same thing on if I tried to put the safety okay on a coil, couldn't do it. It wouldn't allow you. But if you use an in out, you actually get this local data. And so this is the local data. This is the stuff that I'm wanting to mess around with in this in the what's it called? The in this actual function block. So if I go in, remember this is an input. I've tagged it. I have put this data here. So local data, just the same as I would with the flow raw input, pressure raw input. It's the same thing. But inside this block, I can actually modify this data. So like if I look at the status word creation, so local pump data status, so that's local pump, that's what I have called this inside my block. I can actually write to it. And this is an input. And so I can go through and write all of these. So I can move 101 to the status. And the thing about it is, here's another one of those things that I was telling you about earlier, that this 101, what is that? It's meaningless. Well, I could take this. This looks like it's not in local run and it's not in remote control. So we could name that state something, as in it's not running, which is probably what it is. It's been a minute since I've looked at this, but yeah. So if this is local run, it's going to throw 200, and in not remote control, it's going to throw 200. So that means the state of this would be in local control. So we could go up here and add a constant called local control, call it 200, and then change this fixed value of 200 to local control, and it would put that constant value. And then when I come back later at looking at this, and I'm not having to figure out, oh, hey, that's what I was intending by that value. So that's the subtle difference between an in-out and static. Because one thing about multi-instance blocks is that, yes, you can create a multi-instance block, and the instance data block, you get to choose your data block, but you don't always necessarily have access to what you want to call it. So like when I brought this in, yeah, this multi-stage pump control DB is DB2. But if I brought this in on another program where DB2 was always set, then I don't know what would be available for that multi-instance block. And the static memory shows up in the multi-instance data block, whereas this in-out, you're putting it in as an input. And so it makes it to where if you have a process that's already running, that you want to kind of like put your code kind of into the middle of it, then that's where the in-out parameter really comes in, because that can already be there. It has stuff linked in talking into it, and then you're kind of using this data without having to reference, and you can influence this data here without having to change this reference to the static. So at its core though, a multi-instance data block, you can actually change the inputs, or sorry, for an in-out parameter, you can actually modify them. whereas on just a regular input, it's you can't modify them. Normally, you can only modify outputs. And so, like we talked about, I talked about for a second this drive control output. This is intended to be a Telegram 352 output word, and because remember, this is controlling a pump drive, and so all of the stuff in order to control that pump needs to be there. And so our block, not that one, this one, our block has the drive telegram in, and it also has the drive telegram out. And if you're not familiar with that, I mean, we're probably going to set up here on the later part of this this live stream. We're probably going to set up some of this, depending on how long I can go. And so we may talk about that later. So stay tuned. So far, if you've made it to this point, like, and you have any questions about this, and please leave a comment. If you're in chat now and you have any questions or anything like that, drop a comment. But yeah, the in-out parameters are the simplest way to talk about it. Is you can modify whatever you put in on an in-out, but it has like such more subtlety to it. So I'm gonna shift gears a little bit. So if you have any of those questions, be sure to hit me up. But let's go through, and while I do this, see if I can get B17 up and doing something that we can change the project. But yeah, by the way, if you didn't know, Atlanta United, Vamos, ATL, live here in Atlanta, do like to watch some soccer. This year was kind of ups and downs. Had such high hopes, and then the middle of the season just kind of like flattened out, and then couldn't ever get it together. If you watch MLS, yeah, let me know what your home team is in the comments, in the chat. Like, hit it up. But yeah, we've got our golden boy Thiago Almada. He is quite impressive. So let's see, how do we want to do this? So one of the things I had to do was I installed PLCSIM in version 17, and I wanted to test live on a project, a glutton for punishment. I don't know. Maybe I just do this. Maybe we just go through and maybe I just do this and we just wing it. How about that? Project. New project. We're gonna do live stream. We're gonna do load sharing live. Yeah, this might be a mistake. Even after years of working with Siemens, I always doubt myself. But doubting yourself in small things, or I guess in small doses, just means that I feel like it just prevents mistakes. All right, so let's go through. Let's add a PLC. I don't want to limit myself. Actually, yeah, I gotta have a 1500. I want to. Well, no. Now I'm gonna do a 1200 because I want to show y'all something that I found out the other day. We'll do this. Hopefully this doesn't limit me into something. I'll just pick a top end, the top end 1200, which the difference between like a 14, let me make sure, DI 14 in and like a 17, yeah, so that has a couple of different things. So it's really 15 is the one we want to go. DC-DC relay because we're cool like that. Yeah, there we go. So the difference between the 14 and the 15 is just a little bit of power. But we're going to pick this 1515C DC-DC relay. And we are going to, I don't know, try to run PLCSIM. If it doesn't, ooh, this is new. I'm doing this on live, so so all of these settings are helping you prevent all sorts of copy protection, the HMI access to where some of the tricks that I do in some of the other videos, if you haven't checked out my SIP block, so CIP block for Allen Bradley, or sorry, it's a Siemens SIP client block, to where you can actually control Allen Bradley tags on an Allen Bradley PLC without changing the Allen Bradley program at all. If you have the tag names, you can go through and modify tags and like in real time with this block. It's kind of crazy. But anyway, that sort of stuff with secure connections, it's just verifying. There's a little bit more handshaking because yeah, there are some kind of vulnerabilities that you bring into it. So I just want to write a little bit of code. I just want to write a little bit of code about, so if this is on, let's just turn this on, and we'll do like M0.0 here. I just want to try and simulate some very basic stuff. Q0.0. So if I turn this bit on, that goes off. And let's do this I0.0. How about let's swap these? Showing you. So as long as M0.0 is not on, we hit input, it'll turn on that. So this would just be like a momentary light push button sort of thing. So let's see if we can simulate this. All right, we want to do that. Starting simulation, we'll disable all over. Oh, I know this. So what this is doing is it is starting up a virtual PLC here. So this is one of those things that it definitely helps. So this here is the actual virtual PLC. And so when you click that simulate and you have PLCSIM installed, it knows what PLC it would be, and it creates a virtual version of that. The thing about it is this is saying, yeah, the IP address of the device does not match the IP address of the associate certificate, blah, 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 all this stuff. Yeah, because it just created it. So we're just going to trust it because literally the program just made it. But, and so it's going to compile. It's going to compile this device. We're going to download to the device. And that may sound a little weird, but this is actually going through the same process that you have done or you would do on a real PLC. and you're going to click load, and it's going to use the interface that, and then we're going to start the module, because if you notice, it's in it's in stop right now. And so this is the same process that you would have to go through on a regular PLC. And so now this value here is actually, sorry, I've got feedback in my headphones that are kind of distracting me. But anyway, so this PLC works just like a regular PLC. So this Siemens PLC, or the soft PLC, and me shaking it, thank you Windows, I didn't want to do that. But so now we can actually go online with this, and it will act just the same as we are online with another, or with an actual PLC. And so we can monitor, we can check code. Now if you notice, if we were to go in and do like a watch and force table, we can go in and look at M0.0, or I say we can. Am I? Yep. I've clicked too many things at once. I'm still streaming. That is the question. Yeah, but I have done too many things at once. Portal does not like it. Portal does not approve. There we go. It's back. So yeah. All right. So what I was trying to do was go in here and do M0.0, and we can actually monitor just as if we're doing this. And so here we can go through and modify to 1, turn that on, back in our code, do that. So that's that sort of variable table. Now, if I remember correctly, there has to be some way to actually modify the input table, and I don't think you can do that on this. Let's try. You should not be able to force. Is there a way? Modify Control F2. Maybe it will allow you. Yeah, because it's an input, and so it doesn't allow it. So that is the same, because your watch table cannot modify an input. So if you know, if you're in chat and you remember how to actually do the inputs, I'll have to go back through and oh, I see, this is opening up this here. It's been a very long time since I've used PLCSIM. Scan control. I'm looking down here at this bottom. Where is the I/O simulation? Is it the force table? I didn't think the force table could force an input, but maybe I'm wrong. I'm wrong every day. Force 1. Let's go back here. So Lucid gets the Lucid gets the gold star for chat. Way to bail me out. Yeah. So one of the things that we also need to do is make sure stop forcing evolved addresses when we clear the force table. But yeah, because that force table is actually in force, no pun intended. If you do a download to a real PLC, that force table will still be there. So you need to be careful with using the force table. I feel like there was a way in the PLCSIM to have like an input table. And I'm looking through, maybe that's PLCSIM Advanced, because this is the basic. And I may, back from my distributor days when we had all the fancy toys and all the tools, honestly, that was the last time. And that might be an advanced feature to where you actually have a like a list that you can use. But anyway, you can 100% go through and force all these that way. So that is the very quick, very oh, let me do this. See if this works. Let's add in an HMI. It shouldn't, hold on. It shouldn't let me do so remember, anything that Portal will let you do when you are online with a PLC, then it'll do the same thing. So like if it won't let you do something when you're online with a real PLC, it won't let you do it if you were online with a the PLCSIM, the simulated PLC. Is this locked up again? Man, it does not lock it. I'm really pushing it. Clicking too many things too fast. I was gonna add in just like a little basic panel here. Let's throw my favorite, the KTP 700 basic. We have tons and tons of these on the shelf in Alpha's shop because we use them all the time. For if you have just like a simple application that you want to control, the KTP 700, I mean, obviously it's 7 inches. You get a lot of features out of it, and if I remember correctly, it's like, depending on how much your distributor likes you, it's like $700-800 or something or less for this. Whereas a 7-inch comfort panel is going to be probably a little over $1,000. And so we're just going to hit finish on this because what I wanted to do was show you just a little bit of cool stuff. So that's cool. Why do you have all this stuff? Why would I do this? Why does it hate me? All right, I need to stop the PLC. Maybe that'll help not kill my computer. This just goes to show you that I need a full-blown streaming PC. So let's do this. So let's take our PLC tag, because it had a couple of those, right? Get our yeah, I'm gonna have to get off the PLCSIM when we start doing the what's it called, the load sharing. I'm gonna have to kill that thing. So pull up details view, go back to our root screen, go to our tag table, and I want to find that. I'm clicking way too fast. Got too much energy on this random Wednesday. Maybe that's why it's so bad. It has like this reference project is quite large. If that's actually pulled up in this thing, then I'm asking for trouble. Why? All right, there's our tags. Look at those things. Let's So which one was tag 1? Tag 3. So tag 1 is our memory. Tag 3 is our input. So let's do this. Wow. Is normally not this slow. So obviously PLCSIM affects things. So let's pull this and let's actually do this to where properties. Tag 1. Yeah, when I simulate this, it's gonna kill it even more dead. I don't even know if I can simulate this, but we're gonna see, because I think it might require something different. This. It is an output. And then tag 3 was our actual input. Let's try this. I'm killing the stream, unfortunately. It's dying. So I probably need to open less. Anyway, there is a way to actually stream, or not stream, to simulate a HMI as well. You probably shouldn't do it while running all of the streaming software and all of that stuff as well, because this has 32 gig of RAM on it, and it's hurting. So I'm gonna go through. I'm going to close the close that, stop that. I want to see if it'll, all right. So yes, the one thing that happens, I don't need this anymore. Got to get back with the bit rate. Let me check the stream quality. Huh, it looks pretty good. All right, so I was gonna show you that you could simulate the HMI software as well, but I was trying to do a little bit too much. I'll get it set up to where we could do a test of that later. I've just got too many things going right now, and so yeah. So let's go through now and do a little bit more of a shift. If you have any other questions about like PLCSIM, it's pretty basic, or I guess it is simple to use. You just, on the PLC code, you just, instead of download, there's this start simulation, and if you have a license for Portal, you have a license for PLCSIM Basic, and so you just have to install it. And that was one of the things that let me pull this up and show you, because because it wasn't exactly, so like this is the support, this is the support page for the download for all of Portal. Let me get my thoughts together. So if you didn't know this, if you wanted to do a trial of Portal, you can actually download a free trial from the web, free registration. I'm logged in, and here's kind of all of the regular download files. So you would do advanced, unified, all of this stuff, and I did not realize that it used to be that PLCSIM came in that package, and I didn't realize that it did not anymore. And so you have to scroll all the way down to the bottom, and there's this trial download for PLCSIM that is totally separate. So if you already have like version 16, version 17, version 18 installed, you just go to that download page, and there is a download available for PLCSIM specifically. Don't need an additional license. It uses the professional advanced license for that you have for WinCC, or not WinCC, but for Portal. So anyway, that's that. So I'm gonna put that back in, and we are going to talk about. I can close that. We are going to talk about a. Don't want to have any more open than I need. Want to take a bit of a context shift now, and we are going to go and we're going to start talking about a load sharing application, and we are almost exactly an hour in, so let's take a better than coffee break, right? I mean, have to have your sponsored content. Actually, if I was sponsored by Monster, I don't know how it would work. Like, I would just be all over the place. I would just get so much stuff done, but I would never sleep. I had one of these yesterday at like 2 o'clock, and I could not go to sleep until like 2 o'clock. So yeah, cheers to caffeine and other things. All right, let me get shifted over to, I want this guy here, because we are going to be talking about this load sharing stuff, and I want to spend a good bit of time understanding the actual application, because that's one of the things that is some of the most difficult when you're starting out on designing something, is not really fully understanding the application. And one of the cool things about coal mining, and I was talking to a young man, I guess it was yesterday, or maybe another, it was either yesterday or earlier this week at least, that it's like coal mining, people don't understand that there's so much into it. Like, you can go from coal mining and go into any production environment, and you may not know the exact process, and so you'd have to learn the like individual thing, but you will have been exposed to good practices, just because coal mining is just so tough, and so everything's so much more critical, and so yeah, that was a very much a blessing for me. It was also pretty struggle too, because I mean, it is a hard environment. It is long hours. Any sort of production environment, if you're in those production environments, y'all know that 24-hour operations is just can be brutal. And then add on top of that, like, just the nature of heavy industry, it kind of even goes even further. Okay, I got it. Google Drive. But one of the applications that I was talking about earlier was in these mines. You would have these like incredibly long, I guess, the layout of a mine. So you would start, our mines were shaft mines, and basically meaning that there was no way to walk out of our mines. You would go straight down, straight down. Ours were about 2,000 feet down, and then you kind of go out from there. Well, in these mines, you would have main entries that would kind of like go up, and then you would have branches that would branch off. And I'm trying not to to draw the actual layout of the mine, but you would have these different things, and then some of these branches would have more branch, and then it would go off here, and then there would be like areas where they would be cutting out stuff like this, and this is the coal that they would be removing, and they would be kind of going back and forth and removing all this coal. So this is longwall mining. You don't care. No one cares. Not no one. I mean, a lot of people like having power in their houses and stuff like that, and so some people care. But anyway, along these entries, you would have these belts, and I'm drawing them in red, and then you would have belts like this, belts like this, belts like this, belts that would go down here, belts that would go down here, etc., etc. This one would go all the way down here. That. And then, so at each one of these ends, you would have a belt drive, and then this might actually be what would be called like an inline. So this one might go all the way up like that. And then this one would be dumping onto here, and then there would be belt drive here, and this could be, I mean, this distance, it could be a couple miles. So like this could be like 5 miles. Like, I mean, the metric conversion, what would that be, like 8 kilometers, whatever it is. I mean, it could be really far away. It's so far that all of the people and coal would go in here. People would go in and ride up these entries, and to get up to the working faces, sometimes it could be over an hour long just to get to travel up to the working faces to start working. And the coal would travel out from these areas and travel out, fall onto the belt, travel all out, and then get skipped out, meaning there would be a very large 3,000 horsepower, 3,500 horsepower drive system that would be pulling coal up out of these mines. Pretty crazy stuff. But the at each one of these stations here, at these belt drive stations, you would have these really cool semi-redundant drive setups. So let me get a clear screen here. And the way that all of these belt drives would work is you would have 2 rolls. Grab it like this. So this would be like a side view. You would have 2 rolls, and the go down to the header, then it would come back. Make sure to draw this the correct way. Over like that. And then there would be this little setup that's pulling back in order to put tension here between these two. So this would be fixed. This would be moving on like a track. So that's fixed. Yep. And so the coal would be piled up here and be moving down like that. So this would be turning this way. And then this one would be turning this way. Right? Yep. And be moving this coal down through there and out, dumping it onto the next line down. So dumps off there. So comes on, comes down, and then out. And then so this belt, this is the belt drive that we're talking about. And that's the side view. And so when I talk about the belt drive, I'm talking about this whole kind of mechanical setup. And I'll clear this whole thing out. And here's a top view of just the rolls. So you'd have a roll. I'll try to make it a little bit. Have a roll. You'd have gearbox, big fat motor, gearbox, big fat motor. I guess I could draw it like this, but it actually looks like a motor. This is a motor connected. Same thing on this side. Okay, so these are the motors, and all of these, we'll do this. All of these have their motor cables, motor leads coming back to a large belt drive box that has 1, 2, 3, 4 Siemens drives in it. And so in this instance, we would call this would be, we'll call them motor 1, 2, 3, and 4. Okay. So motor 1 and 2 obviously share a shaft. Motor 3 and 4 share a shaft. But depending on the size of the system, these are each these are each 300 to 500 horsepower. Do that conversion somewhere. Where's my calculator? So 500. Nope. 500. So that's then do this just for so we all kind of understand that these are big I did that the total opposite way. How dumb. Did that the opposite. So it's 500 times 0.745. There we go. Oh. 300. All right. So anyway, so we're talking about big motors here, and there's 4 of them, and these were intended to be designed so that at any given time you could have one failure, to where if number 1 failed, the system had redundancy in it. And most of them, honestly, they could run on 2. So they would bring down, they would try to limit the amount of length and coal that's on the belt, so that they could run the belt fully loaded with 2 of these, so that if for some reason they couldn't get a spare or something, then they would have that. And what they would always do is they would always run the system on 3 motors. It would essentially have a safety factor of 2. It had a double safety factor, and they would only ever run 3 motors at the same time. So it sounds a little bit complex of a system, but you could run 4 motors, or all the way down to an unloaded belt. Most of the time would be able to run on just 1 motor. And so you could have anywhere from 1 to 4 motors trying to share a load. And this is a very common sort of thing, to where you have 2 motors, especially like the motors that are sharing a shaft. They kind of are a little bit easier to work with, because they're automatically going to be pulling. They're automatically going to be pretty rigidly linked. But in between these 2 rolls, though, is essentially a spring. Now it's a reinforced mining belt that has like Kevlar weave or whatever in it. Like it's very strong. But if you're aware of mechanical systems and kind of control systems, and then every mechanical system has some sort of spring and dampening to it, and so it's like a spring and a shock. And so in this case, it's mostly spring. So the interaction between the 2 rolls can kind of get a little bit of it annoying. And so how do you do this? Well, if you knew that it was going to be all 4, then you might be able to come up with some scheme of being able to divide out torque and all of that sort of stuff. But you don't. It could be anywhere from 1, meaning no load sharing, because you can just go through and on the HMI just press a button and say disable this one, and what happens is the process to be able to do this is have a primary or master drive. And I always in my mind, so like the previous series of Siemens drives were called the master drives, and so when I say you have to have a master drive, my nerd brain goes to the fact that for decades these were actually running on master drives, and so this conversation was much harder. Anyway, you have a master that you pick, and in this case, let's just pick 1 since it's already done there. And the scheme and the logic is that you're going to take the master and let it run. And so you're going to send it the speed set point. So it gets the speed set point. Okay. And it gets to run at whatever torque or current that it wants to. There's no limit on it. And I'm sorry for the bad handwriting, but it is. So that's what the master. So the master just gets to run. So that takes care of our the case to where there's only one. So if you only wanted to run this system on one drive, you would set it as the master, turn off all the others, and it'd be good to go. Well, because it would be the master. Now, what do the following axes do? So the followers they get the same speed set point, but we're going to modify it a little bit, and we'll talk about why here in a second. They're going to get a speed set point, but they're going to have their torque limited. So one way of doing this would be to just run the following axes in torque control. And sometimes you might want to do that. It's a little bit more responsive because you're taking out a control loop. Sometimes you might want to do that. But the problem is what happens if on a following axis you have a mechanical failure and you lose connection to the load? All of a sudden, this guy starts running away very quickly because it has a torque, and this is a 300 to 500 horsepower drive. This is a very powerful motor. And so if all of a sudden it goes from requiring, say, just random number, 1,000 Newton meters of torque, and this breaks, all of a sudden it takes off running. There's nothing to stop it. So what this setup is called a saturated speed controller. So what we're going to do is we're going to leave the speed controller in it, so if there is a mechanical failure, it doesn't run away. At most, it's going to run at some speed set point. So that's why this stays in, is because we assume that at some point something catastrophic is going to happen. And in a coal mine, it absolutely will. You can put a coal miner in a locked room with a steel ball and a rubber hammer, and you'll come in and the steel ball will be cracked in half. Coal mines are rough. And so you have to assume that things are going to break. And so we leave the speed controller in there, so at most it's going to tap out and run at the speed set point. There is a problem though with this, because when if you are not, so what happens, let's talk for a second just about what happens when your speed controller, you will get a speed set point. We'll do this in like let's do it some other color. You'll get some speed set point, and that our speed of our drive will come up, and it will try to track that set point like that. Well, the thing about it is if you aren't trying to run faster than the master, then the follower won't ever actually take any load, because especially in the case where there's number 2 here, number 2, what'll happen is number 1 will get this running up to speed. Number 1 has the ability to run at whatever, and so it may or may not actually share any load. And the whole purpose of this is to make sure that it's sharing a load. The only way that the in a case with the speed, both speed set points being the same, the only way that it would actually be able to share the load would be if it couldn't achieve the speed. And the second that it achieves the speed, it's not gonna share the load, because it one axis is going to take more, and it's basically going to run at 100%, and the other one is only going to run a very small percentage to pick it up, and it could be random of which one it is. So you're never going to get good load sharing. So what you actually want to do is have the follower always trying to essentially give out 100% torque. And that sounds totally backwards, but you want it to where this speed set point can never actually be achieved. And here's why. Because what we're going to do is, let me see if I can get some of this stuff going. So what we're going to do is we're going to take the speed set point, and then we're going to add to it, say, plus 5%. Let's say that. That means that at most, if this was running, if our speed set point for this was 70% speed, we are going to take and pass this down, and so that'll be 75%. So if left alone and not torque limited, the drive number 2 would always take 100% of the load. It would always take 100% of the load. It would put out as much as it possibly could, get current limited, and then drive 1 would kind of just bump it up a little bit. So what we're going to do is we're going to take the torque actual value from the master and set it as the torque limit. So torque limit equals master torque actual. Now, so what that means is that as the master starts to accelerate, so up to the set point speed, we want it to look something like that. Our torque value is going to be up here, and then hopefully it will settle down at some fixed value. Well, so this is the actual torque value. And so if you think about this master torque here, the master torque actual value being set at the torque limit, and we know that essentially this follower is always going to be trying run essentially at 100% torque. Because if we know that, say, 100 Newton meters, say this is 100 Newton meters of or 1,000 Newton meters of torque. If we know that that's how much it takes to do this load, then as the master's torque actual goes up, the follower will automatically start taking exactly the same amount of torque that the master is putting out. Because it's always trying to outrun, and so it's always trying to catch up. And torque is used to accelerate a load, and the follower is always trying to accelerate. It's always trying to speed up. It is never satisfied. And so what will happen is, in our new torque, as this goes up, our follower will also go up. So this orange line, our follower, will be delayed just a little bit, but it will also go up, and the torque required from the master will eventually start to come down. So like this will start to creep down. And what will end up is you will end up with both of them at some value that is pretty close to half. And so this is on like a 2-axis system. And so essentially all we're trying to do, so just as a review, the master gets whatever the actual speed, and it gets 100% torque. The follower gets the same speed set point, but we're going to add in a 5% or so addition to it. And then we're going to take the torque limit and cap down on it. And the torque limit is going to be whatever the master's value is. So just as a review, the follower is going to always be trying to run faster than the master. The master is going to be essentially limiting the speed of the follower by limiting the available torque available to the motor. Cool thing about this setup is you can set up this pretty simply, especially in like an S120 type setup. You can actually pass these values back and forth on the CU320-2 directly. You don't even actually, you definitely wouldn't need a PLC if you were using to do this type of load sharing. Changing over between masters and all of that stuff, that would be a little bit more difficult. But what's really cool about this is it scales. So if you have 2 followers, then it will automatically split the maximum torque required. In our case, in this little example, it'd be 1,000 Newton meters. It would split it into thirds. And so each the master, as it starts trying to accelerate that 1,000 Newton meter, you have now 2 drives that will be running at whatever that is. And so it'll kind of come up, and then it will stabilize because it'll start to move to where, all right, it's getting up to the speed, and it's like, all right, the master will see, essentially it doesn't know about the followers. And so it just says, oh, I don't actually need as much torque anymore, so I'm going to bring down my torque, and that's automatically going to limit however many followers it is. If you have 2 of them, then they're going to be putting out the exact same, and you'll split it into thirds. If you have 3 followers, then it'll split into quarters, and this works really well. So let's go through, and if you have any questions about this, I'm gonna leave this available, but I'm gonna go into Portal, and I'm gonna go into Portal, and hopefully set up a little bit of a system here to be able to right. Yep. So let's go in and Portal is really not liking me today. The goal would be to go in and actually set this up. Let's close some of this stuff out. So I want to go in and I'm just going to set up a really quick S120 system. We'll just do two axes on this. And I want to set this up and sorry if I don't talk as much during this and I'm just clicking. I'm trying to run through things quickly enough to where I can control units. I want to do it that way. I want to do. So we'll do I don't want to do a servo though. That's what I was kind of trying to avoid. Let me do this then. I'm not gonna do this. I'm gonna do S120. Redo. We're gonna do two G120s. It'll be simpler to show the process. I'll do another video. I'll do another video where we actually go through an S120 and show you how to do it without having to have a PLC involved. So Lucid here says if master goes into regen for whatever reason and you send negative torque limit in the positive direction, what happens at that point? So you're not actually sending I'll show you that Lucid, because you're not actually you're going to be doing a multiplier, and you're going to be instead of sending a negative torque or sending a torque limit, you're going to be modifying a percent of a percent modifier. So I'll show you. We'll definitely take care of that. So you brought up a very valid point. If you send a negative torque limit into the positive limit, you could get a runaway condition, because instead of trying to achieve that torque limit, essentially it takes away the torque limit. And so if it ever actually gets into a situation to where it wants torque, it will shoot up and run away. And so Lucid here is asking about how to prevent that. And we're gonna I'll show you that. So let's just do a couple of G120s because they're a little bit simpler to get going, and they don't have the servo mode or servo control, which means I did this again. You always gotta. Literally did this yesterday. I picked the wrong one. Which means you have to kind of go in and set by default. By default, S120s are set up in servo, and for this example, I want I want them to be in vector control. And so and I also want telegram configuration. I don't want 1, I want 352. Reason I'm picking 352 in a second is that there is a, I say that I don't have it in here, but we're gonna pull this up here in a second. So let's do drive 1, power units, PM240-2, 3-phase. We'll just go with frame size D, middle of the road. We're in the US, so we're going to use a 37 kW unfiltered. Is we may not have a solid ground. If you're not aware of this, if you were using a Dynamics a G120, so the PM240-2 power module, either for a G120 or an S120 system, you want to get the unfiltered version if you're in the US for a couple of reasons. One, the 480 volt voltage. If there's any sort of like high voltage, like voltage increase, it puts a lot of stress on the filter, the EMC filter that is on the kind of built in. So like this version, this A version has an EMC filter that's required in Europe. But if you're building in the US, not only is it not required, it's not recommended because of the higher voltage. And if you were in some sort of heavy industrial plant to where your ground is not a solid ground, it is highly recommended to not only to get the unfiltered version, but some of the larger frame sizes, like the frame size G, only has the C3 filter, but there's a grounding screw on that to remove that. And there's a lot of issues that can come up with that. Most of it has to do with noise, which sounds crazy that an EMC filter would create noise, but it tends to cause issues if you use a filtered version of these power modules in the US. So we've got our 2 power modules set up. Let's go through, save this in case we crash. And so what we're going to do now, we've got our 352 telegram. I want to show you in the drives where you would go to actually set these channels. So I'm going to set up, in this case, drive 1 as the master and 2 as the follower. And then at the end, if we have a little bit of time, I will talk a little bit about how you can make that kind of like in the mining system. You had 4, how you can actually kind of balance those out, or swap on the fly, I should say. So in our set point channel, our speed set point comes in here. The easiest way, if you are using a PLC, is you're going to use the same kind of control path for the master. So it essentially gets to do whatever it wants. So the master, you have your main set point coming in here. Then your main set point scaling is 100%. You don't have any additional percent set point, and no limits on your torque. So that's the master. And I'll show you torque limits right here under operating mode, torque limitation. And what we're going to be messing with is this scaling. And this scaling is pretty easy to always make an absolute value. So if you're scaling, if you're using your scale value instead of actually putting in to the upper torque limit here, changing that, changing this scale value, it's much safer because it's much easier just to do an absolute value of whatever, and then you're not ever having to worry about if you are scaling into the wrong value. And I'll show you this on here in a second. So those are the 2 points. We're not going to touch those for the master, but we are going to look at in our communication transmit. Remember, in the drive, once you're into start drive, this is all from the perspective of the drive. So the drive is transmitting this data out. And here, the reason I went and changed to that 352 telegram is because of this right here. By default, it puts torque actual value into the transmit data. So we can actually see this. This is R80.1, so that is PZD4. Now, how do we actually get this to what we are actually wanting? And from receive. All right, we're on the master. So we see that because we picked that 352 telegram, we have the stuff that we want, because we're going to be sending the following axis a speed set point and the master's actual torque value. And so those are the 2 things. And I just wanted to show you that selecting that 352 telegram is actually the way that we get that data. You can use a 999, a free telegram, and kind of put these in. I have blocks that I use, like in my agriculture library, that has the what's it called, the 352 telegram in it, and it's because of this. So we can do load sharing. So what I'm going to do on drive number 2, which let's just go ahead and rename this to follower. And I guess technically I'm supposed to be not saying master. I'm supposed to say lead axis, but I'm a boomer. So the follower, let's go into the following axis configuration. And now what we are going to do is, if we know that this axis is always going to be the following, and essentially you're never going to have a case to where you're swapping like we set up before, we can go to frequency speed set point, and we can just put in an additional set point here. And if we go down here, I want to say that there is a fixed value 5%. Look at that. And I know I did that pretty quick, but I am wanting to, in my set point path for my follower, add in an additional 5%. And if you're just joining us in on the chat, to reminder, we're trying to make our follower constantly outrun the master. And then we're going to limit the torque that is available to the follower to be able to do that to whatever the master's torque value is. And eventually, they'll pretty quickly even out and be pretty dead on. So what I did here is I'm going into the set point channel of the follower and adding in a fixed value of 5%. So that is 5% of max value. Now, this might not be the best way to do it, but this is how it's the easiest way to do it. And if we have a little bit of time, I may talk about why it might not be the best way to do it. So if you're not aware, down in the parameter 2900 has a bunch of just values that you can put into BICO connections to be able to just common values 5, 10, 20, 50, 100, 150, 200%, so that you can kind of go through and you can fix values in your system if you're just wanting to add stuff. There is also another value, parameter 2930. If you don't have one of those values that you like, you can always use parameter 2930, and I want to say that parameter 2931 is the actual value for that. So like that's the oh, sorry, no, this is the actual parameter. So yeah, so parameter 2930, not R2902, parameter 2930, you can actually set a value. So if you want like 12%, you can put that 2930, you can put 12% into 2930 and use it. They don't give you a lot of that because, I mean, this is a basic drive, but you can still do a lot with this basic drive. So we're going to go swap that back to 5%. So now this will always try to be on a 1700 RPM or 1750 RPM motor. It will always be trying to run 170 RPM faster than the master. What this might cause is on startup, that might be a little bit too much of an offset, because at slow speeds, it'll cause like a boom. It'll actually like hit pretty hard on the follower. So that's why I say if you're doing this in like a real application, you might want to figure out a little bit different way of doing this. And honestly, you might want to use a user-defined PZD value to put that in here. And again, if you have any questions about what we're doing, where we're doing this, just drop them in the chat, drop a comment. Maybe you have a question about like what is a good value. Normally you need at least 3%, 3 to 5% more speed of your master of the actual set point. You want at least 3 to 5% more, and so that just makes it to where your PID controller absolutely stays saturated, which meaning the output from the speed controller is always 100% torque. It's always trying to run as fast as it can, because if you don't do that, it's not going to load share. It might drop off, and then the master will take up more load, and you don't want to do that. So the second thing we have to do, so we've got our additional speed set point in here. It's trying to outrun the master at all times. We need to now limit that torque limit. And so one of the things that we will have to do is we will need to go in, let's just look at the torque limitation, and we're going to try and do this upper torque limit. And like Lucid mentioned here just a second ago, there is a consideration for slowing down as well. You don't want all of the braking power. Well, you may not want all of the braking power in the master. If you don't set the negative torque limit and kind of set it up on the opposite side as well, then there's some issues that can come up with that as well. Sometimes you might only have one braking resistor, and you want to always be using that motor, and so you would set that motor up as the master, and then you would set the following axis up to a negative, like 0 negative torque, and then that way they could not brake. Because the worst thing that you can do, and there are situations where you can do this, is you can get in this kind of like inverted state to where this scheme will set up and it will balance out, but you actually have the following axis pulling against the master axis. And we probably wouldn't get into that right now, but just know that there is a a way that that can happen during acceleration that if you're not handling things quite right, if you don't get that saturation um, that we're talking about, like that, if you don't give it enough offset speed, it'll actually, the master will take off, and then the follower will actually like pull down. It's just, it's weird. But then once they hit steady state, they come back and everybody's happy. But anyway, that was a tangent. We're talking about the upper torque limit scaling. So what we want to do is we actually want to get this from the master. And in G120s, that has to be passed from the PLC. So the PLC, through the telegram, is going to pass it into the both the master and the follower. So in order to get the torque limit for the following axis, it has to go up to the PLC from the master and then down to the follower from the PLC. So it takes 2 cycles. And so we're actually going to be looking into Profi Drive receive words. And so these are the 2050s, and we don't know quite which one to pick right now. So what we're going to do is we're going to cancel out of that, but we know that we're wanting to put that master torque actual value that we looked up just a second ago, we're wanting to get it back into the follower. So we're going to cancel that, go back to communication and receive direction. Remember, again, this is from the perspective of the drive. This is what is being received from the PLC. Cool thing about the 352 telegram is you have the main set point, and that's it. So you have 1, 2, 3, 4 user defined. It's set up as a 6-6, 6 in, 6 out, but you can have all of these user defined values here. And so what we're actually going to do is we are going to use this third PZD as the value for our, what's it called? For our torque limit scaling. So this is our 2050 index 2. And if you notice that, so I'm just hovering over what that is, and that is our 2050 index 2. And so that is Profi Drive PZD receive word PZD3. So we're going to put 2050 index 2 into our drive. So let's go back to torque limit, upper torque limit, and we're going to change this to PZD 2050 index 2, just like that. Now, remember, we're going to make sure that this value is always positive when it's coming back to us. We're going to say okay, and honestly, for the basic part, that is it. Now you are going to have to go through. I'm going to go through and show more about the PLC side of it here in a second. But you're still going to have to tune your drive. And one of the things about this is you want this drive to be fairly responsive, because if it is not responsive to the speed controller, then it's not going to be able to saturate, and you're going to run into issues under acceleration that we kind of talked about before. And so let's go through and now look at a couple of little things. What I'm going to do is I'm going to open up a global library, because I have not a new, I have a library that already has the 352 telegram defined, and I just want to grab that PLC data type because of where are my types? There they are. I just want to grab this there, out there, and I'm gonna drag this over into all these over into new data types. I'll show you why here in a second. So I'll show you, it's a pretty easy way to set up these tags. So in my network view for the master, I see that here, the 264, 275. So 264 to 275 are those. So I'm gonna go to my default tag table. Get rid of all these. It's gonna hate me in main, but whatever. So I'm gonna say master drive in, drive out, in, data types 352 in. Oh, la, 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 la. Got to compile. Okay, and then gotta compile when you bring the stuff in. Anyway, and I'm gonna change this. So I'm just making these 352 in, 352 out. And now, so these need to be those values that we saw over here, which blah 264. So we're gonna go here, I264.0, and we do it that way because the first, it's not an IW, it is an I, because the first part of this telegram is bitwise, and so otherwise sometimes it doesn't like like doing that. So now we're gonna do Q264.0 as well, and then we're gonna go back over here, and we are going to 276. That's on both of them. 276.0. Q276.0. Now, I just so happen to, because like I said, these telegrams, I have this PLC data type set up because I like to do torque limiting, and I like to do load sharing, and I like to do all this stuff. And so look at this, I already have them set up for these tags. So the third word of the out, so now this is the PLC perspective, so this is going out to the drive. I already have that PZD3 set. So upper torque limit is already set to PZD3, and so that's going to be in that the 16348. So 0 to 100% is 0 to 16348, and then you have a sign bit, and then you can go all the way up to 250%, or I guess 200%. You double it. So that's why that 16348 value is because it's 16 bits. Then you have 1 bit for the sign, 1 bit for the sign, 1 bit for 200%, and then so what's left is 14. So 14 bits is 16348. So now with that set up, we have in our follower axis, in our torque limit, upper torque limit, we have our upper torque limit scaling is that percent that we're coming from our PLC. So let's go in and let's just look at how you would do this. Let's delete this because it's red. So we would have some value. We'll just do m 0.0. We'll say that's always on, even if it's not. Right now, I guess it would be like this. We're gonna move our move 16.348. This is the very like rudimentary process for this, because I mean 16.348 we're going to go and let's see, we're gonna move, let's make some tag let's just do it this way, mword 10. So that's going to be a word, that's going to be 16-bit, and then that's going to be I'll show you how we do this. I'm blocking that with my head. Don't know why. Alright, so master drive in, master drive out. Speed set point. We're going to drag this here. Why? Not like that. Whatever. We'll just do it this way. I was going to show you how to do it that way, but we'll just do it that way. And then we're going to copy that. PLC. We want those going to the same place to follower drive out at speed set point. So that's sending out that speed set point. Now, obviously, I don't have any of the control words and stuff like that, like the off one, off twos, like all of that getting sent out. So you would have to do that. But now all you would have to do, so there we are sending our two speed set points. And now what you are going to do down here is you are going to move the master drive in actual torque into follower drive out upper torque limit. Bam, done. Ship it. It's a little bit more complicated than that, but that's the basic principle of it. Obviously, this is for a very specific set, but at this setup, once you go through and actually get all of your off ones and off twos and all the speed set points and all of, or not speed set point, but the values for like what's it called, your control word, which we can look at that real quick. So the let's do follower drive out control word. You have all of these bits. You need to have control by PLC on, have the no code stop, no quick stop on, enable operation, enable ramp function, unfreeze ramp, enable set point. You basically have to have all of these values here on, and then you would turn the value, enable the drive, make it run, would be controlled by this bit here. Now, I hand waved over a lot, but look at how I've done this UD or the custom data type. And if you got questions about that, I think I've brought that up on some other stuff, but these custom data types are really nice, and hopefully I'm glad the whole library thing worked really well, because I didn't practice that before, but I've done it many times. But that's really basically it to get a load sharing application. And there's a lot more to that, and there's a lot of kind of finesse about what can go on with these values. So like I talked about before, the biggest thing is you want your follower to stay jammed up. And so what's coming out of this where is it? The speed controller right here. What is coming out of here on this speed controller? This is your speed set point. Remember, on the follower, we want that always to be higher than the master axis. So that's why we put that 5% in. With the what's it called? I'm losing my train of thought. With the master, it gets to run whatever it is. We always want the follower to be not able. So this should always be whatever 100% torque is. If it's not, so if you're troubleshooting something and they're not load sharing, especially under acceleration, you may not have enough offset, or your motors aren't tuned properly. Like your speed controller's not tuned hot enough. Your following axis can in general be tuned a little bit hotter, so this P gain factor can be a little bit higher. The integrator time can be a little bit lower, and so one of the other things as well is pre-control. If you're not familiar with what that is, it's inertia compensation. If you're using inertia compensation, it can get a little bit weird in some of this, because remember, you're wanting to tune, or inertia compensation is like, it compensates for known accelerating torque. Well, from the master's perspective, it doesn't know about the following axis. Remember, we said that before. And so if you have one following axis, it thinks it's seeing, say, half of the real torque. If you have two, you're going to be seeing a third of the real torque. If you have three, then you're going to be seeing a fourth. So pre-control really messes up these type of systems, because you could actually see like an inversion of the master's torque, and then kind of like we talked about before, you get this hit from the following axis actually trying to pull the master axis. It's some weird stuff. So just know that, go ahead and tune the master axis without pre-control at first, because it does not know about that. So one of the other things that I guess we could talk about, or I mean, we're already over 2 hours, but I do want to talk about it, kind of go back to my sketch pad, is a reminder that this spring, this kind of spring that we talked about here, in between these rolls, the way that comes into effect is by essentially delaying getting, if these are followers, which obviously they would be, number 2 drive here kind of has an easier time of number 2 drive has an easier time of matching the speed of 1, because it's mechanically coupled, but 3 and 4 are mechanically coupled by a spring. So number 1 may not, so this roller has a spring in between this roller. And so what may happen if you get to where you don't have the speed controllers on 3 and 4 completely saturated, that spring starts to take into effect, and you'll see oscillations in between the 2 axes, because and it'll be in the speed. Obviously, it'll be in the torque as well, but you'll see these kind of oscillations, and it could be caused by this spring. The worst part, though, I promise you, is under acceleration, and it's this interaction. It's this interaction right here. If your orange line here cannot follow that green line exactly, then I say the orange line because that's the torque. But if the speeds aren't exactly matched, say if your master is trying to outrun the following axis, it'll at best master will pull 100%, and then the follower will kind of put in a little bit, maybe like 5-10. But usually what happens is you get a situation. Let me go ahead and do this. You get a situation to where I will draw. So this is speed, time. I'll draw the master. Let's do it this way. So blue line is set point. So set point is going to follow some ramp function and then off like that. So that's set point. Let's look at what our red, green, blue. Yeah, well, if our master follows that fairly well and goes up and kind of sits like that, we can get that type of tune on it in terms of speed. The biggest problem that I have seen is if you have a following axis that has a different ramp function rate. So say that this is a 5-second time period. Why would I put 5? That's because let's say this is a 4-second time interval, and we have a 6-second on our following. What happens with that? What happens is this is the situation that I was talking about, to where if this is on this set, so like between 1 and 2, then you will get a situation to where the following axis will actually be running in negative torque. So it will be fighting against the master. And so if you sized it appropriately, then the master has enough torque to be able to pull like a negative 20%, but it's gonna be being slowed down, and so it's gonna pull it out, and then like it's just this weird situation to where what you'll see is the master value will be like 60% torque, the follower will be like negative 20, and then when they're at steady state, they sit there at both at 30%, and they're both at 30% in the steady state. And that's because you have two different ramp functions. So if you take this and make it 4 seconds, and then you change this to where it's trying to run this, but it's actually trying to run up to a higher speed, then it load shares a lot better. It's really it's really actually a little bit better to have this at least 4. If you have the ability to like always have one master and then always have one follower, then you would actually want to put this acceleration time down even further to say 3 seconds, because then that means this value will be like this, and it will be forced exactly onto the master's speed, which is kind of what you're wanting, because it's really going to be, that's really going to lock it in really fast. But yeah, so this setup again is a saturated speed controller, torque limited setup. So worst case happens, you get your follower runs a few hundred RPM faster than the master if there's a mechanical breakage. So, and that's really all there is to this little setup. I mean, we've been going for about 2 hours and 20 minutes now on this. It's been a nice little live stream. Hopefully I've gone through and on this application explained kind of the nuances of what's going on here, because I personally think that this is one of the cooler applications, because you can take this setup, scale it from 2 all the way up to 20 if you wanted to, and the only differences that you're going to have to be worrying about is this spring and how the systems are connected together. I've done this same type of setup on what's it called, steel mills, where they have like thin sheets, and they've like split the coils, and they're doing rolled pipe and welded pipe, and so they're taking a flat sheet and rolling it up, and those rollers, it goes from a long flat sheet to a rolled pipe, and they're welding it up at the top, and in that process it has a bunch of motors, and they're all load sharing, and they have like, they're pinched down, and you're all load sharing. In that case, that is a very rigid connection between the two. So if you have a torque ripple on this motor, then it is going to directly affect and fight up against the upstream and downstream. And so that's what that springiness talks about. So if you got questions, comments, or whatever, like definitely feel free to like. Well, if it's helpful, if this has been a good stream, or I mean, really, if you come across it and you want to see more of it, like the stream. Feel free to comment on if you're watching this on demand. I'll go through the comments. The community is fairly tight knit now. We've got some people that kind of watch these streams and watch all our videos, and I hope that as you come on, you find these things helpful and start communicating back and forth and commenting and asking these questions. And these live streams are for you. They are for these comments. All 3 of these, the things that we did today, were from comments on other videos. And so it may take me a minute to get to them, but I try to comment back as quickly as possible. And then as we do more and more of these live streams, absolutely we'll bring up more and more of these topics. So leave your comments, and yeah, if you've come here and you're not subscribed and you're watching this, definitely subscribe if you want to know and be able to participate in these live. Be sure to hit the bell, because that will actually send out a notification when I go live. We had a few people on this one the whole time, and we had some highs and lows, and so it's good to see everybody during the week. I've noticed though that probably Friday morning seems like this would be the best time to do these, and so I'm going to be traveling this Friday. That's why I didn't do it on Friday. But maybe next Friday works out. If that would work out for you, drop a comment to see if it would work out. But if not, if you're in the US, have a happy Thanksgiving and holiday season. If you are not, have a great rest of your week, and just always keep learning. And yeah, look to see you next time. See ya.